Okay, welcome to my video on titration. What I want to do in this titration video is tell you a little bit about what titration is, first of all, and then how to do calculations and how this might work in a lab situation, in a lab problem. First of all, titration is a situation where it's a natural extension of the solution chemistry problems that I was just doing, the solution stoichiometry. And what I do in a titration is I generally have an unknown concentration of one reactant and a known concentration of the other. And what I do then is I add them until I know I've kind of hit an equivalence point where I have as much of the one as the other in my reactant. They've basically canceled each other out. In the case of this formula that I'm doing, this first one I'm doing, this is an acid-base titration. Potassium hydroxide is a base, which means its pH is between 7 and 14. Nitric acid obviously is an acid, and its pH is between 0 and 7. So what I can do is I can basically, if one of these is known and one of these is unknown, from the balanced equation, I know my molar ratio is 1 to 1. Well, if the solution is basic, then my pH is going to be above 7. If my solution is acidic, then I know that my pH will be below 7. So what I can do is whichever my known one is, I can put that in, I can add the unknown or vice versa. Typically you add the known, and then what I can do is add it until this pH will go to 7. At that point, I know I have as much of this as I do of this, and they kind of cancel each other out. What that allows me to do then is if I know the concentration of one of them and I know the volume, I can figure out the number of moles of that, I can figure out the number of moles of the other, and as long as I know the volume of this other one, this unknown, I can take the number of moles divided by that volume, and then I can get the concentration of that unknown. So the whole key is you need to know when you have equal amounts, when an equivalence point, when these things have kind of canceled out, and then using that knowledge you can determine the moles of your unknown, because you'll know the moles of your known and you'll know the molar ratio, and therefore you can figure out the concentration of your unknown. And that's kind of the whole point of a titration. Now, so that you understand how this works, typically you use two burettes or a burette and something that allows you to measure the volume exactly of the other one. But if you'll notice, these burettes start with their numbering at 0 and work their way down, typically to 50. Typically they're pretty long, and they have a valve here, and you can see an actual picture of that valve. And basically what you do is you put an indicator of some sort to let you know when you've hit this equivalence point into your unknown. So you add a known amount of your unknown, a known volume, add your indicator, and then you add your known solution until you get that change. Let you know, in this case, maybe if I'm dealing in acid base, that I've hit a pH of 7, so that I'm at a neutral point. And then I can go through the calculations I'm about to do. So it's basically it's a stoichiometry problem, but it involves an unknown material, and you're simply trying to find the concentration of that unknown material. So let me show you how this works, and there's a couple different ways to look at the problems, and I'd like to show you several ways, and different ones may work for you. If you look at this one, this is my known. They're giving me a known volume at a known concentration. And again, if you remember from my previous video, molarity is equal to moles per liter of solution. So if I take the number of liters times the molarity, I will know the number of moles of my material. So in this particular case, and let me just do that here, if I have for the KOH, if I have 1.50 molar solution, and I multiply that by my volume in liters, which would be 0.1398 liters, I'm going to find then that the number of moles of KOH that reacted, and let me check here, was 0.2097 moles. So as I did my reaction, this is how much KOH I added. This was my known material. I added it, and I got perhaps my indicator color change, which let me know, okay, I'm at equivalence. These things have canceled out. To do that, I know that I needed 0.2097 moles of KOH. The thing is, I can look at my balanced equation, and I know that for every 1 mole of this, I'm going to react with 1 mole of this. So if I have 0.2097 moles of the KOH, I know that that reacted with exactly 0.2097 moles of HNO3. So going backwards, if I know that I had 0.2097 moles of HNO3, and I know that that was contained in 50 milliliters of HNO3, or 0.050 liters. If I take the number of moles divided by the number of liters, I'm going to get the concentration of my unknown, which is actually what I'm after here. And in this case, I'm going to get 4.194 molar. So that what I've done then is I've used the fact that I knew the concentration of this, I mixed it myself, and I added it until I hit the equivalence point to determine the number of moles of the other, divide it by its volume, which I read off the side of the burette, or if I've added it previously, I just measure how much I've added, and then I can determine the concentration. Now what this represents then is kind of a solution stoichiometry way of doing this, where you figure out moles of one thing, use your mole to mole ratio, and then find moles of the other thing. You could do this whole thing with a dimensional analysis or factor label setup, and I always tell my students just start with what's given and that sort of a thing, and so we'd have 0.1398 liters of basically solution. I guess I would write that out. And then what I'm going to do is I know the molarity is 1.50, and that is moles of KOH per 1 liter solution, because that's what molarity is. It's moles per liter of solution. So this then liters will cancel, and so if I take this times this, that'll give me the number of moles. Well, notice that's kind of what I did here. And then in the next step, what I'm going to do is I'm going to go from moles of what I started with to moles of what I'm trying to find, and in this case it's the HNO3. And again, this is my molar bridge, my molar relationship between one thing in the equation and the other. So if I stop now, I now will have moles of HNO3, but of course I want to know the molarity, which is moles per liter, so I'm going to have to put 0.0500, right? Yeah, that's liters. So what will happen here is liters will cancel. I might as well just do it. Liters will cancel, moles will cancel, so I'll be left with moles of HNO3 per liters of, and I guess I should write HNO3. And if you do the math on this, in fact, you can see you're going to get basically the same thing. You're going to get 0.1398 times 1.50 gives you the 0.2097 times 1 over 1 is still 0.2097, and then you're going to divide it by 0.05. So that would be kind of the dimensional analysis way of doing it. Now let me show you another problem. This is a little more set up like the results you would actually get in a lab situation. Let me just do this in red so we have a little variety and you can see the different formats. First thing you need to do is you need to recognize that the way burettes are recorded is, and I mentioned this a moment ago, you start from 0 and you count down. So if I start at 20 and then take it, or 10 in this case, and take it down to say 30, then the amount of liquid I've added would be 20 milliliters. So you generally with titrations record the starting and the final volume, which are the readings on the burette, and the difference of course is then the volume that was used. So in this particular case, if you look at it, you're going to take the 49.2 minus the 11 and you're going to get, I believe, 38.2 milliliters of strontium hydroxide being added, and then for this guy here you're going to take 38.6 minus 5, and of course you're going to get 33.6 milliliters of this material. So that is my amounts that I'm using. Again, they were given to you up here, but this is what the actual data would look like. And other than that, the problem is basically the same sort of a problem, but I do need my balanced equation, and so let me give you the balanced equation in this case. Let's see, my reactants are strontium hydroxide. I don't want to run out of room down below for my calculations, so let me try and squeeze this in up here. SrOH2 plus perchloric acid, HClO4. Okay, and then this is going to be producing the strontium perchlorate. Let's see, so that's Sr, and that's plus 2, and then I'm going to need 2 of the, because of the -1 charge, I'm going to need 2 of the perchlorate ions. So let's do this, ClO4, and I've got 2 of them, and then I've got HOH again, which is water, H2O. And now to balance this, I'm going to need a 2 here, 2 H's, and a 2, no, I have a 2 in front of the H2O, I'm sorry. Yeah, I'm just going back and forth counting mentally. And so I think I have everything there. So now I have a balanced equation. Now notice the difference here. My relationship here is 1 to 1. Here my relationship is 1 to 2. So this complicates things just slightly, but I want to show you how you would do it. Again, going back to the dimensional analysis, and I can go that way for the whole thing. Start with what's given. I know that I had 33.6 milliliters, or 0.0336 liters, and this is of my HClO4 solution. I'm just going to do solution here, times, and again, liters moles, my molarity is 0.202. So I've got 0.202, make sure that's obvious, per 1. So again, basically what I'm doing is I'm multiplying the volume of the known material times its concentration. By multiplying that out, that will give me, the liters will cancel, and I will be given then the moles of the HClO4. And let me maybe put that up here so that's obvious. Now I can go from moles of HClO4 to moles of SrOH2, but notice here in my balanced equation, this is a 2 to 1 relationship. So I've got, or 1 to 2, I should say, I said that backwards. And again, these come from the coefficients. So what this means is, once I know the number of moles of this, I really have to cut it in half to get the number of moles of this. And so that makes some sense. Then when I'm done with this, of course, I will now know the moles of strontium hydroxide. I'm trying to find the concentration of the strontium hydroxide, so I'm going to divide that by that volume, which is 0.0382 liters. Make sure that's kind of obvious. And then when I do this whole problem, I do the calculation, I got 0.0888 moles, because it's moles per liter, or molarity, or capital M, however you want to do that. So that would be, and this is my strontium hydroxide. Okay, so then that is kind of how you do the titrations. And again, just like up here, I could really do this first step here kind of separate to get the number of moles of HClO4, recognizing it's a 2 to 1 relationship, divide it and cut it in half, divide it by 2. That gives me the moles of this. Once I know the moles of this, divide by the volume of the hydroxide, and then again you will get the molarity of the hydroxide. Now, one other thing I just do want to show you is you could also set these up using a different formula here, which some folks like to use, and it's a personal preference. Of my the one I'm trying to find, some people call it the analyte. The thing I'm trying to find, the concentration of that would be equal to the concentration of the titrant, the thing I do know, times the volume of the titrant, times your molar ratio. And again, that molar ratio is going to be the analyte, the one you're trying to find, over the one you do know, the titrant, the one you're adding to it. Okay, and then this would be divided by the volume of the analyte, and again, that's analyte is the one you're analyzing, or the one you're trying to find. So let me just show you how this would work for this particular problem. The concentration of my titrant, the one I'm adding in this particular case, is given to me as 0.202. The volume of it, and again, I'm going to convert it to liters, so I'm still going to call it the 0.0336. But you really don't have to, because the conversion will cancel out. You don't really have to do that in both cases, but I'm going to just kind of show it to you. And then again, for the molar ratio, my molar ratio is the one I'm trying to find, the strontium hydroxide, which is 1, over the titrant, the one I'm adding that I know is 2. And notice how this really matches what I've done here already. And then you divide that by the one you're trying to the one you're trying to analyze, the analyte, and that is going to be 0.0382. And again, if I do this, I'm still going to get 0.0888 molar. And as I mentioned, as far as the volumes, you could leave these both in liters if you want, because again, the mathematics will cancel out. But that's a preference for some folks. I just like to do it in liters because that's the correct way to do it. I mean, it truly is, molarity is in liters. So again, a couple different ways to do it. One is to convert to moles, look at your relationship, and then find your final thing, divide by the volume. You could do the whole thing in a dimensional analysis type of a way, or you could use this formula, and basically you're finding the concentration of what you're looking for, the thing you're going to, will be equal to the one you know, the concentration times the volume of what you know, times the molar ratio over the volume. So hope these help.